So basically, I want to speak about two more or less unrelated topics, and the best of a title I could come up with this title because the two topics deal with quantum mechanical system and trying to explore and exploit similarities. But then that's it somehow. So my talk will be separated more or less in two independent parts. So you have seen yesterday Hassan's starter, and I do the same here. So basically, I don't have to repeat the numbers for those who have seen Hassan's slides. I just want to back up also with the statistics of allocated CPU hours in supercomputing centers, and the numbers are similar if you go from one center to the other one. Physics, material science, and chemistry usually take a large portion of allocated CPU hours. Yet the mathematics of it is completely, at least for those for this topic of DFT, for instance, is completely underrepresented. All right, and nevertheless, many of the key challenges of the 21st century are related to atomistic simulations like drug design, finding new materials, and energy storage. Okay, so the outline of this talk is the following. As I said, there are two parts. And I speak first about ab initio molecular dynamics using Hartree-Fock or DFT models, using a technique that we call Grassmann extrapolation. And the other one is we switch to quantum spin models. And I speak about the reduced basis method for quantum spin models. Okay, of course, this is not work on my own. So the first part is joint work with Geneviève Toussaint, Filippo Liparini, that we just heard before, and Etienne Pollack, while the second part is joint work with Michael Herbst, Matteo Rizzi, and Stefan Wessel. Okay, so let's start the first part. So we have, thanks to Filippo, we have seen an introduction on this equation. So I start with these equations straight from the beginning. You can think of a DFT nonlinear eigenvalue problem, or also the Hartree-Fock, depending on the taste you want to give it. So this is already discretized in a finite dimensional basis set, and then these are the Euler-Lagrange or first order optimality conditions of the constrained energy minimization problem. So to highlight here, the red parts are given data, so that is problem depending, and all that is blue is a solution. Okay, so here you have the Fock operator or the DFT operator that is given by a density independent part and the density dependent part. So this is the single particle operator and usually the bioelectronics integrals here if it were Hartree-Fock, or all density related contributions if it were DFT. S is the overlap or mass matrix here. Okay. All right, so as we have just wonderfully seen in the previous talk, this nonlinear equation needs to be solved, and the usual approach is SCF iterations, where you start with a guess density, and then you solve subsequent linear eigenvalue problems, and you hope to converge. Okay, so a good initial guess, as you can easily see, can reduce the number of iterations drastically. So if you have a good guess that is close to what you're looking at, you only have a few iterations to do. On the top of that, what was also be discussed in the previous talks, you have a large slew of different acceleration techniques. Often they are the same or slightly similar techniques like Dice, charge mixing, Poulai mixing, or Anderson acceleration. And the typical characteristic of these eigenvalue problems is that the number of orbitals or eigenvalues that you're looking for is proportional to n, the number of electrons, which is proportional to the number of basis functions. Wait, there should be one n should be here. So everything basically is proportional. The number of basis functions, the number of electrons, and the number of nuclei. So m is the number of nuclei, n is the number of electrons in the systems. Okay, a plain plain SCF implementation without any trig scales up to n4, as we just heard before. Of course, you can considerably reduce this with many tricks, but let's say this is an upper scale of the asymptotic costs of a SCF iteration. Okay, but on top of this, if you do a molecular dynamics simulation or geometry optimization, you have to solve this this eigenvalue problem for many different but yet similar molecular situations. So here we focus on the density matrix. So it's CC transposed, and for simplicity here, I'm assuming that I have an orthonormal basis, so S is identity. Otherwise, you have this constraint here. There's the normality constraint in terms of functions that translates into a different scalar in a product with the S matrix in the discrete case when you discretize. Anyways, we assume S to be identity here. And then this D has a certain nice or a number of nice properties. It's self-adjoint. Here we assume just real algebra, no complex numbers. It's idempotent, or is a projector, so D squared is equal to D. It's a rank N matrix, and it's invariant under orthogonal transformation of the basis of, or the representation of the molecular orbitals. So if you take an orthogonal matrix, you multiply C from the right, and then you build the density matrix, you get exactly the same density matrix. So this motivates to introduce what is isomorphic to the Grassmann manifold, which is this set of matrices of dimension NB times NB that fulfill all these properties. And yes, so this is a D represent, or is a spectral projector on a subspace of R and B, and one subspace does not depend on a specific basis to represent the subspace, and this is exactly represented by this invariance on the orthogonal transformation. So in terms of algebra, the Grassmann manifold is the quotient space of the Stiefel manifold with unitary transformations or orthogonal transformations. Okay, as I have already shown in the tutorial, there is a locally bijective mapping between the manifold itself and, for a given point on the manifold, its tangent space here. And you can map using the logarithm from the manifold onto the tangent space, and you have a representative vector in the tangent space. And if you apply the so-called Grassmann exponential, you map this down back on the manifold. Okay, more than that, if you take the scalar parameter going from 0, so here from this point to there in a continuous fashion here, and you look at the exponential here, this parametrizes a curve on the manifold, and this is exactly the geodesic linking the D0 with the D. And this is not just a fancy tool from Riemannian geometry, but you can actually compute this exponential and logarithm function. What you need to do is, it's a bit complicated, but what is limiting is somehow for either operation, logarithm or exponential, you have to do a SVD of some matrix. Okay, and so this is the asymptotic cost is the number of basis function times n square. Since n is smaller than nb, you take the square on the n. Okay, so this can be computed, and it's, let's say, in the same order of magnitude than SCF computation, if you assume that your SCF computation is cubic in the number of basis functions. Okay, now we switch to a setting where we have a parametrized eigenvalue problem. So I introduced this parameter P, and P is a parameter in some parameter space. So then you have some input data here that are parametrized, and then you want to solve this eigenvalue problem, and you have the solution. Okay, so for instance, here is one normal mode and you have a one-dimensional parameter where you can switch the mode, and the nuclei changes according to this normal mode. Okay, so this could be, this parameter can be a reaction coordinate, collective variable, or whatever you call it, or also the script of the nuclear coordinates. So we can now introduce the solution submanifold. That is, we vary this parameter, and this varies, if it's a one-dimensional parameter, it curves a line here on the manifold. And this is this D here. Okay, so that's the object of interest. And now we do a first application. And before I explain you what we're doing, we ask you a fundamental question. So you are now in a vector space. So in Euclidean geometry, you have 2 points in your Euclidean space, and you know that there are the function values for 2 parameters, P1 and P2, and you ask yourself, what is the function value or an approximation of it for the parameter value that is in the middle of the 2? Well, easy guess, you take a straight line, you put yourself in the middle, and that you call the approximation. So this is linear interpolation, okay? But the straight line is indeed the geodesic, so the shortest path linking those 2 data points. So you can do exactly the same on the manifold. And in this case, when you know you have 2 density matrices for 2 parameter values, and you ask yourself, what is the density matrix for the parameter point in the middle of these 2 points, P1 and P2, you take the geodesic of 1/2. Okay, and I previously showed you how you can do this. Yeah, so now the more general question is, we have n density matrices on the manifold, and how can we inter or extrapolate? So the first question that can be thought of is, I have a one-dimensional function. So P is now just a one-dimensional parameter, and it parametrizes this one-dimensional curve on the manifold. And we have this density matrices computed by some means, and we have some distant points, and they are accessible. How do I interpolate on the manifold this curve? So what you can do, and since this is very messy here I just draw the vectors in the tangent space. You can build the tangent space at some representative density matrix D0. You compute the logarithms, so these are vectors, and now the tangent space, and that's what I use in this first part all the way, is that the tangent space is always a vector space. It's a Euclidean space, and we can apply all kinds of standard techniques. So since we have this P of i's, I can define the Lagrange polynomials with the properties that if I evaluate this as Bj, I get a delta Kronecker delta ij. Then you can interpolate here a new vector in the tangent space by evaluating or taking the Legendre polynomials as a function of P times the gamma i's. And then you take this approximation and you project it back using the exponential on the manifold. And very nicely, because exponential and logarithm are bijective, at least locally, if you evaluate the dn, this approximation in Pj, you have the exponential of this linear combination. But this turns out to be a delta ij. So this sum reduces to gamma j. But gamma j originally was mapped from di, and this is is identity. So you are exactly interpolating on the manifold. Okay, so you can ask yourself, how well does this work? So what we take is we take an equilibrium position and we compute one of the normal modes by diagonalizing the Hessian in the nuclear coordinates. And this is this global collective vibration. So it's a low frequency. And we tested on 4 different compounds here with different number of atoms, orbitals, degrees of freedom, etc. Okay, and then we interpolate and see how does the error reduce if we take more and more interpolation points. And you see exponential convergence. and that you have very decent accuracies. So this is the accuracy in the density matrix. So, and we use this as an initial guess to launch afterwards a SCF computation. And here we trace the number of SCF iterations we require using the this interpolation with a certain number of data points or pre-computed density matrices. And you see you can bring it down to in the order of 1 to 3 SCF computations that you can achieve by doing this interpolation. So just with 5 snapshots, we have almost a perfectly converged SCF. Okay, you can extend this to no, I thought we can extend it as 2 dimensions, but you can extend it to 2 dimensions, but apparently there's a different presentations. Please apologize. So we switch to the second application, which the first one is limited somehow. It can only work with a small number of parameters. And now we are focusing on general Born-Oppenheimer molecular dynamics. Okay, so you propagate the nuclei R according to Newton's second law. And for at each time step, you need to solve the DFT equation for a given position of the parameter. Okay. Now the question is, I have pre-computed densities and I have a time dynamics. How do I give an accurate guess at the next time step? So this is more like extrapolation. And so we are given, therefore, a set of previously computed density matrices, and we want to have an accurate guess at the next step, dn+1. Okay, so our answer is that we apparently, or at first sight, make it more complicated than it is, but we split the whole thing in 3 different mappings. So the first mapping, and it will have its purpose, I explain that in a minute, maps the nuclear coordinate in a descriptor space. Okay, so we are embed the atomic position in a possibly very high dimensional space. So this is an explicitly given mapping. Then from there, and that's the mapping we want to learn, we want to map on the tangent space before we apply the Grassmann exponential to map down to have a guaranteed density matrix. Okay, now this is explicit. This is explicit. So the only unknown mapping that we need to learn or approximate is this red mapping here. And please note, this is a mapping between 2 vector spaces or Euclidean spaces. So you can apply standard tools. Okay. So here, just as to memorize, that's the mapping of interest. So what we have now given is we have previous descriptors corresponding to previous density matrices that we can map on the tangent space. And these are then the representative points in the tangent space. And we're given a new descriptor, dn+1, because we have evolved the nuclear coordinates. So we know the nuclear coordinates, and now we have to compute the electronic structure for these coordinates. Our answer is that the new representative point at step n+1 is a linear combination of the previous ones with some coefficients, and there are solutions to this minimization problem. So here we aim to approximate the new descriptor with the same linear combination that we use here of the previous descriptors, plus some regularity term that turns out to be useful if you take many snapshots. Okay, then you solve this problem, you get the CI, you insert it here, you get the gamma n+1, then you apply the exponential, and then you have a new guess for the density matrix. So why would that work? So first part is you have to think of what happens if this mapping was linear. So gamma n+1 is by definition this mapping of the descriptor n+1. Okay. Now this dn+1 is close to this linear combination. So with some error that is controlled by this quantity to be minimized, I can replace this here. Okay. Then if f is linear, and there's a big if, but if it were linear, you can play the linearity trick, and that's the linear combination of the images of the di's, and the images of the di's are obviously the gamma i's. So this one is a good approximation of this with one error that is induced by this, but under the assumption that f is linear. Of course, in practice, this is not the case that f is linear, but it turns out that it's very useful to map the nuclear coordinate in a very high dimensional Hilbert space. And then this mapping from the descriptor space to the tangent space is much easier approximated with a linear mapping, because this is one of the messages we learned from machine learning. Then if you embed your data in a high dimensional Hilbert space, for instance, you can much more easily separate one part of the data from the other one. So you can also more easily approximate this mapping. So there are two errors. One is this not being identically to 0, and second, f not being linear in practice. Okay, so here are the numerical results. So we run a trajectory, and here we have this first data have a threshold for the SCF at 10 to the minus 5, and we run this on 4 different compounds. So these are production runs in the group of PISA, so there are no artificial systems. There is a QM-MM system, so here you have the number of QM atoms and MM atoms and the number of basis functions for the QM part. As a descriptor, we take the simple Coulomb matrix, and here we trace the average number of SCF iterations for different strategies and the standard deviation. So this is the normal extended Lagrange Born-Oppenheimer prediction. So you use the extended Lagrange technique in order to generate an initial guess. And this MW means McQueenie purification, which is a projector of the density matrix onto the manifold. So this, you see, this improves quite, well, at least for the first two systems, improves the average number of SCF iterations. So GX with the number here in the bracket means with 3, 4, 5, or 6 previous density matrices that you take into account in your fitting process. And you see that in some systems you can have a drastic reduction. In some, it's a bit less prominent here. And in particular, if you go to a threshold that is tighter in these first 3 systems, you have a drastic improvement of SCF time, whereas here you only have a slight improvement, but we have no idea, to be honest, why this is the case. Okay, so these are 2000 time steps, so it's a picosecond trajectory. So there are hours per iterations, and the largest system took 25 days on a 28 class cluster. So a reduction for, let's say, 10 to 40% in absolute times can mean days or even weeks. Okay, short part on a short and long-term drift. So the problem we are encountering now is, compared to XLBO that controls time reversibility in a sophisticated manner, it more or less, compared to our results, at least for low threshold of 10 to the minus 5, has very good conservation of energy, where we have here a long-term drift. The short-term fluctuations are about the same. It's really in the long-term drift. However, if we increase the tolerance to 10 to the minus 7, we have a good agreement. But currently, work in progress is to put time reversibility in our procedure as well. Okay, so I summarize part 1. So this geometrical structure of the Grassmann manifold can be computationally exploited to provide structure preserving initial guesses for SCF iterations. Combined with molecular descriptors, this provides an effective tool at moderate costs. And our first simulation showed that it outperforms the state of the art, especially for tight convergence thresholds. As I said, this is just the first step. So we want to enforce in our guesses some kind of time reversibility in order to enhance the stability, and also to apply this to geometry optimization, where you cannot use the extended Lagrangian technique. Okay, that was part one. And these are the references on this framework. Okay, as promised, we completely switch gears. So if you were bored by now, it's time to wake up and maybe give it another chance, because we switch the topic. So now we come in a more, we are in a more discrete case, because we have now n-sized quantum particles, and each has two states here. We can generalize the methodology to more than two states, but that's what we have looked at so far. And so the many-body quantum states belong to Hilbert space of exponential complexity. So if I add one particle, the dimension of the Hilbert space doubles. Okay, so we look in a generalized setting. We say, again, we have a parametrized problem. We have a parameter mu. And I'm looking for every mu. I'm looking at the ground state, or possibly ground states, because the methodology allows degenerate ground states, corresponding to the smallest eigenvalue lambda of a Hamiltonian. And I give some examples of Hamiltonians just afterwards. And once you have solved that, you're interested in expectation value of some observables. Okay, so what we assume, which is typical in the reduced basis framework, and what is called affine decomposition in the reduced basis framework, is that the Hamiltonian here can be written as a linear combination of parameter-dependent scalar functions times parameter-independent Hamiltonians. Okay, and possibly the Q should be unrelated to the number of particles. And we do the same assumption on the output function. All right, so the first example is a chain of excited Rydberg atoms. Don't ask me too much about the physics, but you have here atoms, and they can be in an excited state or in a non-excited state. And there are models for dealing with that. And so you have here, these are single particle operators. You have the Pauli X matrix here. You have here this Rydberg excitation operators. So this comes from a laser field that excites excites the particles. And here you want to enforce all of them to be excited. But you have some out to the -6 van der Waals repulsion if two states are excited on the same atoms that are close. This gives a large energy contribution. Okay, but essentially we have two parameters here. We have this ratio of what is called the detuning parameter over the Rabi frequency, and here this NS is related to the Rydberg blockade radius. Okay, and naturally you see we have this affine decomposition. So this gives you one Hamiltonian, this second, and the third one. Okay, and the observable is the so-called structure factor, which can be written up like this. And it is some kind of a Fourier analysis on your wave vector to see in which state you are. Okay, we will see nice pictures afterwards that are based on the structure factor, and that gives a nice somehow explanation of what this means. I don't have much intuition with that. Okay, so this second model is an antiferromagnetic spin 1/2 triangle model. Please apologize the technical details here, but you have some unit cell, and unit cell you have 3 spins. And it's called a frustrated spin model because they want to be in opposite states, but you have an odd number of them, so it is always frustrated. So you have the stronger interactions through these 3 parameters and the weaker nearest neighbor interaction J prime. with periodic boundary conditions here. Okay. And yeah, again, you can write this in this affine decomposition with three functions here and three independent Hamiltonians. Okay. So now here we have three parameters. So this normalized by J3. Okay. So what is the solution manifold? The solution manifold, we already had an introduction earlier tonight by, today for you, by Ivo Made. And so this is the set of all solutions of the problem. So here's the eigenvalue problem. So it's all ground stage and the variation of the parameter. And the working hypothesis here is that despite the exponential increase of the Hilbert space, the solution exhibits a high linear dependency for similar parameter values. Thus, a low dimensional basis with n basis functions in this and curly n dimensional Hilbert space should exist such that the span of this basis so well approximates any member of the solution manifolds, and n should be moderate with respect to curly n. So this sounds like crazy if you have a quantum system with an exponentially increasing dimension and you have entanglement and all crazy things. However, if you run the first dummy examples that were explained by Ivo as the SVD, so that's the first test you usually do before you go to a more sophisticated technique like the greedy sampling. If you just sample your parameter space with a test grid, and for each sample point, you compute the ground states, and then you assemble this matrix and you look at the decay of the eigenvalues. What you see for a number of particles ranging from 7 to 13, these SVD profiles tell you how linearly independent are or dependent are the solutions. That only increases moderately. Okay, so you kind of expect. So for 13 particles, if you take dumb thing here, if you take 75 basis functions, you expect an accuracy about 10 to the minus 3. Okay, so if you do that for 7 particles and want to have 10 to the minus 3, you expect about 30 basis functions. Okay, now it increases. Okay, and here is for a threshold of the 10 to the minus 3. Here you see how it increases with the number of particles. However, and note, this is a log plot here, a log plot. That's the dimension of the Hilbert space. The ratio of the explored where the solution manifold lives to the overall dimension of the Hilbert space, this becomes smaller and smaller. Okay, so it's more worth to exploit these reduced bases. Okay, but in practice, you don't want to first sample all the possible ground states and then compress them to find the basis. You want to be smarter, as explained by Ivo, and this is kind of, you use a greedy problem. Okay, so you want to obtain this basis at feasible cost. And what means feasible cost? If you have an n-dimensional basis, you want to only solve n eigenvalue problems, truth solves or high fidelity solves in this high dimensional space. And you can do this by this briefly explained greedy strategy. So you start with an initial basis, and let's say you are a given small n-dimensional basis. You project your Hamiltonian into that basis. Okay, so this is a n times n matrix. You solve this eigenvalue problem for the mu. There's an n-dimensional eigenvalue problem that goes relatively quickly. You then have still a training set, but you only evaluate this residual and you pick as next sample point the one that maximizes this error surrogate. So you kind of then embed the solution here, you represent it with the high dimensional basis, and you compute the residual on the full Hilbert space. And then you have different accuracies for different mu's, and you take the one that is least approximated, you compute the snapshot here, and you build a new basis. So this is a bit the simplified version, because in practice, you have to care about degenerate states, and you have to orthogonalize the different snapshots and in order to avoid stability issues. But on a on a one page, that's it. Now, in order to do this efficiently afterwards, you can, once the basis is known, and this also applies at every step n here, once you have the basis for the next round, you can pre-compute this parameter independent Hamiltonian, since they do not depend. You do this once, and if B has an n-dimensional basis, this is an n times n matrix. You do the same for the basis if it's not off-normal for stability reasons and with the output function. Then, if you are given any new parameter, you have this pre-computed small h's, and you can just rebuild this sum. That's an operation that is independent on curly n, on the high dimensional. You can solve this in a complexity that's independent on the full Hilbert space. And you can solve that. And then also you can compute the output functional in a complexity independent on curly n. And so here's an example. So we consider a Rydberg chain with 13 sides. And you see here, that's the error surrogate that steers the greedy. And for academic purpose, we also computed the real error here in the density matrix. That's a formalism to deal nicely with degenerate states, and the error in the eigenvalue. And as usual, we see that the eigenvalue error is about twice the convergence rate for the eigenvector. And also the output functional converges faster. And so here, these are the two parameters for the Rydberg chain. And here, that's an error profile in log plot for the final state at 100. And you see where the greedy samples, and it kind of samples at the physically important points. And then you can look what happens with this occupation number plot. So here, the intensity of this point is the maximal occupation number of your wave vector. So the darker it is, the more it is in one of the, it has the highest occupation in one entry only. So it's closer to a pure state. And so here, as you go for n to 20, you know, this is definitely not the same than this one. But here at n30, you already no longer, at least in the picture I, in the picture norm, distinguish the plots. And so for the next plot, it's important to have this line, because I show some plots along those lines. And you can associate this state to certain orders. So this is the slightly not scaled. So this one should be this one. The C3 states are this one, and the C4 are this state. So if you look which state is actually is the argmax here, then you see it's the C4 here and the C3 and the C2. Okay, and then if you compute the structure factor, so here you have a wave vector along this line, and you see here you have a very sharp transition that is reflected here. You see that here this spectral information about the wave vector has one peak. So this is the C1 phase here, because it's periodic over the boundary of 2 peaks, 3 peaks. That's the 3C state, C3 state, and 4 peaks. Periodic is the C4 peak. And you see, so the truth here is with these squares. Can I zoom that in? Yeah. Or not the squares, is the crosses here. And you see, you started with a reduced basis from 2. That's complete crap. And then 4 is okay. And with n reduced basis functions, it's already a quite decent structure factor. Okay, so this was the second part and the end. So the idea was to use reduced order modeling, which allows also to work on quantum spin systems with exponentially increasing Hilbert spaces. So this is applicable to a wide family of problems. Usually quantum systems, spin systems have always this affine decomposition where you have some parameters of interactions times some Hamiltonians. And surprisingly, this solution manifold can be described accurately by only a few snapshots, despite the fact that your Hilbert space is exponentially increasing, and the greedy algorithm allows the identification of suitable snapshots automatically that are physically relevant. As I said, the methodology can also handle degenerate ground states. And so the next step we're working with in the framework of a massive thesis is now to allow the RBM technology for the truth solves to use a DMRG solver to reach much larger number of particles, because right now we use what physicists call direct diagonalization, which is not or exact diagonalization, which is not exact, but which is just a plain Lanczos, or in our case LOP PCG algorithm. So that's the reference. I thank for your attention, and you can read this completely unrelated message below here. I'm happy to take questions. Thank you.